Okay, so we'll start. Uh, so four people are here, right? Yeah, can you guys see my screen? Yeah. So I am Diljit Dutta. So I am a research scholar in Indian Institute of Science. So I will be taking this session for the course Hydraulic Engineering, which is being taught by Muhammad Saud Afzal. So in this session, we'll be solving some sample questions that will help you in solving assignment 0 and assignment 1. So yeah. So the whatever the video I take, with like whatever I teach in the Google Meet links, Google Meet, it will be uploaded in my YouTube channel. And yeah, so you can, I will send a link for the YouTube channel. It is given here. I will send this PPT. So you will find all the videos under the playlist CE35 Hydraulic Engineering. And there are two books that I recommend for self-study. One is this Hydraulics and Fluid Mechanics, including hydraulic machines, by P.N. Modi and S.M. Seth. And the second book is Hydraulic Engineering by Robertson and Cassidy. So let's proceed. So I will be sharing my other screen where I will be like. So I will be projecting my screen from my tab where I will be writing. Yeah, so you can see my tab screen, right? So this is where I'll be like solving the questions. So can you just give a yes or no in chat, or just tell anyone of you can tell me that if you can see my screen. Okay, yeah. So yeah, let's proceed. So first of all, I hope you guys are taught about the specific gravity, mass density, specific volume. What are these concepts? These concepts are being taught, I think. 1 second, I will just full screen. Okay, I hope these concepts are taught. So based on these concepts only, the first question is based the specific gravity of a liquid. So there are three main definitions. One is first thing is specific weight. Specific specific weight is given by the formula weight of the fluid divided by volume of the fluid. So this is one thing. So the specific gravity, and then the second thing is specific volume. The specific volume is given by the reverse of specific weight, so it is volume of the fluid divided by weight of the fluid. This can also be given for gases and compressible fluid. This is also given by the formula 1 divided by inverse of mass density, that is rho, mass density of fluid. So now what is specific gravity? So specific gravity of a fluid is given by specific weight of the fluid divided by specific weight of water at 4 degrees centigrade. This thing is very important. You have to mind that the specific weight of water at 4 degrees centigrade. Why 4 degrees centigrade? So this is important because only at that temperature we can say that the density of water is around like 1000 kg per meter cube. When the temperature of the water changes, the density also of water also changes. So we can take 1000 kg per meter cube as density of water only at 4 degrees centigrade. So this is the standardized standardized way of measuring specific weight of water. So so what is the unit of specific gravity? So unit of specific gravity will be what? So it is a ratio of two specific weights, so it will have no unit. So the first question will go as no unit. So yeah, I hope you have understood. It is very simple, I think. The second question, it's also a very basic question based on definition only. So this question is based on what is compressibility beta and bulk modulus K. So you know what is bulk modulus K. So the bulk modulus is given by minus of dP by dV by V. So rate of change of difference in pressure divided by rate of change of volume with respect to initial volume. Why minus? So this minus sign is given for the formula of bulk modulus because if you increase the volume, the pressure in the if you increase the volume of a fluid element, so in that case the pressure of the fluid element will be decreasing. So to keep the ratio of dP and dV as positive, to keep the bulk modulus as positive value, we have included a negative sign in the formula. And the compressibility is given as compressibility beta is given as 1 by K. So this is a very basic formula. It is given, you can find in any standard book. So here this beta is equal to 1 by K. Okay. So next, coming to question number 3. So so this question is about no slip condition. So first of all, we should know that there are two types of fluid. One is the ideal fluid and the second is the real fluid. So what is the ideal fluid? Ideal fluid is given as a fluid that that is incompressible, that doesn't have viscosity, that is mu equal to 0. So there is no shear between layers of fluid. So these are the two prime criteria when you define a ideal fluid. So that is the shear stress for an ideal fluid is equal to 0. So now when you say about no slip condition, so thing is that suppose we consider a rigid boundary. So this boundary is like, you can see it is smooth, but if you see at the microstructure of the boundary, so there is small undulations on the boundary. So when there are small undulations, I am just showing it to magnify. One second. I am just showing it to magnify the effect of the boundary. So like when a fluid is flowing this way, So this is direction of fluid flow. So if a fluid is flowing in this direction, so there will be like many molecules of fluid. So these molecules of the fluid will be interacting with the rigid boundary, and the molecules that are attached just near to the boundary, so they won't be moving. So they will be like attached, they'll get attached to the boundary by adhesive forces. You know, adhesive forces is like the force of attraction between fluid and a and a solid substance. So these particles will be sticking to the boundary, and the particles only on top of that will be moving. So the what is a no slip condition? So the no slip condition is like when we take a real fluid that has like it is compressible, and also the shear stress is not equal to 0. So it is a function of rate of shear strain du by. So this, suppose this is just for Newtonian fluid you are saying, it can be any power. This is just considered linear part. If we don't even consider linear relation between shear stress and the rate of shear strain, then also it is a real fluid. So I am just taking the very simple criteria of the Newtonian fluid. So the shear stress is non-zero. So in that case, so when you take a fluid, so the thing is that when the particles of the fluid interacting with the rigid boundary are not moving, so this will try to oppose the fluid motion. So you can, the fluid is moving in this way, so it will try to give a resisting force in the opposite direction. So this resisting force will be like it will be very high near the boundary, and this slightly diminish as you go away from the boundary. So the force, you can see it will be highest here, and it is going it will diminish as we move away from the boundary. So this phenomenon only gives rise to boundary layer. So that will come later in the course. So whenever it comes, we will teach you later. So the no slip condition, this is called a no slip condition, that when a real fluid is flowing over rigid boundary, the particles of the fluid will interact with the roughness of the surface, and the particles just near the surface won't be moving. So these particles will have V equal to 0. Wow, 1 second, sorry. So yeah, so these particles will have V equal to 0. So this phenomenon is called the no slip condition. So it is valid for all real fluids. Okay, so I hope you have understood this thing. If you have any doubt, you can ask me. Okay, so this is called no slip condition, and this only gives rise to this boundary layer theory, and that is valid for all real fluids. Now coming to the next question, that is it is based on viscosity of a fluid. So the viscosity of a fluid in motion is 1 poise. So what will be its viscosity when the fluid is at rest? The thing is that the viscosity of a fluid, the property of the fluid, the viscosity of a static fluid or a fluid in motion, it's the same. So the property of a fluid, intrinsic property of the fluid, can never change. So whether a fluid is in motion or a fluid is at rest, it doesn't matter. So the viscosity will be 1 poise, be whether the fluid is at rest or the fluid is in motion. So for this question, the correct answer will be C, where the viscosity doesn't depend on the type of the fluid motion, be the so it, because it is a, so mu, that is a dynamic viscosity, it is a property of a fluid. And this depends on the type of the fluid, like, and also it also depends on the temperature. So there are two things. So for liquid, when the liquid, if the temperature increases for a liquid, the mu will for a liquid, if temperature increases, mu will decrease. Why is that so? So if we increase the temperature for a liquid, the shear stress between the liquid, the molecules the shear stress between the molecules in the liquid, it will be decreasing. So there will be less momentum transfer between the two layers of the liquid, and this will cause decrease in the dynamic viscosity of the liquid. And secondly, for gas, so gases, so if we increase the temperature for gases, the mu will increase. Why is that so? So if we increase the temperature of gases, the molecules are like very far apart. So if we increase the temperature of the gas, the entropy will increase. So the molecules will go into very random motion, and they will interact, and they will collide with each other. So in that case, when the molecules are colliding more in gases, so in that case the viscosity of the gas will be increasing as we increase the temperature of the gas. So this is how the viscosity of a fluid, be it a gas or a liquid, will change. But it won't change when the fluid is in motion or a fluid is at rest. So it depends on only two criteria. So I hope this thing is clear. So now next, moving to question number 5. So this is a numerical question. So there it is given that the 3 liters of petrol weighs 23.7 Newton. Calculate the specific gravity of petrol. So let's start from the basics. So what is the volume? Volume equals to 3 liter, and you know 1 liter equal to 10 to the power minus 3 meter cube. 3 into 10 to the power minus 3 meter cube. And what is the weight? Weight equals to 23.7 Newton. So now, so what is the specific gravity? So the specific gravity is given as specific weight of the fluid divided by specific weight of water. And what is the formula for specific weight? Specific weight is, so I am writing at set what is specific weight. Specific weight is given as weight by volume. So what is weight by volume? What is the weight? Weight is equal to m into g divided by volume. And what is mass? Mass you can write in terms of volume. So mass equal to rho into volume into g divided by volume. So if we cancel volume, so this comes as, one sec. So if we cancel volume by volume, from numerator and denominator we get as rho g. So this is specific weight. So now what is specific weight of water? So it is rho water into g on the specific weight of the petrol, that is rho petrol into g. So we can cancel G with G, right? So how will we know rho of water at 4 degrees centigrade? This is important. So rho of water at 4 degrees centigrade is 1000 kg per meter cube. Now what is rho of petrol? So rho is given, we can find by rho by specific weight divided by G. So how will you proceed? So specific weight of the fluid you can also so the thing is that rho of petrol will be equal to mass of petrol divided by volume petrol. So what is the volume of the petrol that is given? Volume is 3 into 10 to the power minus 3, it is given, and mass of petrol will be weight of petrol divided by G. Weight is 23.7 divided by 9.81, it is 1000. So you can see 10 to the power minus 3 and 1000 will be cancelling, so it will be 23.7 by 3 into 9.81. So if you do the calculation, this value will come as 0.805. So specific gravity. So this will come as 0.805. This is how you solve this question. I hope this is clear. If there are any doubts, don't hesitate, you can simply ask me. Okay, so now moving on to the next question. The oil of dynamic viscosity having 0.125 kg per meter second and specific gravity of 0.80. What is the kinematic viscosity in meter square per second? So first let us note down what is given to us. Dynamic viscosity means mu is given, that is 0.125 kg per meter second. And what else is given? Second thing that is given is specific gravity. Specific gravity is given, and that value is given as 0.80. So what do we have to find? We have to find kinematic viscosity. So kinematic viscosity, nu is given as mu by rho. So we have got mu, so we just need rho. So this we have to find out based on specific gravity. So how will you find rho of the fluid? So the formula for specific gravity is, so you can just come from here to here. So specific weight of the oil divided by specific weight of water equal to 0.80. So the specific weight is given as rho into G. So rho of oil into G and rho of, and one more thing, just for your information, I am saying that the value of G we are taking as 9.81. So the thing is a standard value, like with, but if we move to the pole from the equator, there will be slight variation in the value of G. So in that case, if we take a fluid at equator and the fluid at at pole, in either case the specific weight will be varying, but for sake of simplicity, we will be taking G as 9.81 throughout the course. So we won't be taking the variation of G in this course. G in solving the numericals. So yeah, so G and G will be cancelling, So how will you get? So rho of oil equal to 0.8 into rho water, and rho of water is equal to 1000. So it is 800 kg per meter cube. So we have got rho of oil. So we have obtained value of rho of oil. So now what do we need? So we need to find kinematic viscosity, that is mu by rho. So mu equals to, what is the value of mu? Is 0.125 kg per meter second divided by 800 kg per meter cube. So if you solve this, if you find the values, then it will come approx, I think, 1.56 into 10 to the power minus 4 meter cube, meter square per second. So this is how you solve. I hope there are no doubts in this numerical. If there are any doubts, don't just ask. Okay. So coming to the next question. So it is given that 1 liter of a certain fluid weighs 4 Newton. What is its specific volume? So now the specific volume, we mentioned that it is given as inverse of mass density, equal to 1 by rho. So 1 by rho of the fluid, whatever fluid you are taking. So based on that given information only, we have to find the value of rho. So what is given? The first thing that is given is volume. Volume is given as 1 liter, which is equal to 10 to the power minus 3. So one important thing, always while solving a numerical, it is always important to note the units, so that everything is in same unit. If you don't change the units to the same SI unit or like centimeter that unit, and then all your numericals will be wrong. So always first keep everything, transform all the values to all the units, all the whatever parameters to same unit, then only start solving the numerical. So the volume is given as 1 liter. 1 liter is equal to 10 to the power minus 3 meter cube. So and the weight of the fluid is weight is given as 4 Newton. So what do we need? We need first, if we have the weight and volume, we can find the specific weight. So what is specific weight? Specific weight is given as weight by volume, which is equal to 4 Newton divided by volume is 10 to the power minus 3. And Newton, you know, mass into acceleration, so mass equal to kg meter second square. So these are all in same units, so it will be 4000 Okay, so if we have specific weight, So the specific weight is also given as rho into g. So this we have seen earlier also, specific weight is given as rho into g. So you know the value of g, so g is 9.81. so how will can get rho equal to 4000 by 9.81, and the value of density, the density units mass by volume, that is kg per meter cube. So we have rho. So what do we need? We just need to find the inverse. So specific volume is inverse of rho. So specific volume equals to 1 by rho is equal to 9.81 divided by 4000. So again here, if we solve, 4000 3 zeros can be it will come as 10 to the minus 3. If we divide 9.81 by 4, it will come as 2.45 into 10 to the power minus 3 meter cube per kg. This is how you find the specific volume. Okay, I hope there are no doubts until now. Okay. Coming to question number 8. A fluid occupies around 4 meter cube of volume. Calculate the specific gravity of the fluid if the fluid mass is 12 kg. Okay, this is again similar type of question. So first let us note down volume. It is given as 4 meter cube, and the mass of the fluid is given as 12 kg. So we need to find out the specific gravity. So just let me specific. To find the specific gravity, we first need to know the formula. Formula is specific weight of the fluid specific weight of water. Okay, so so what is the specific weight of the fluid? Just move this little bit down. The specific weight of the fluid is given as rho into g, or weight of the fluid divided by volume of the fluid. So it is given as specific weight of water is rho water into g, and for specific weight of the fluid we won't be writing in terms of rho and g. We will take the initial formula, that is weight of the fluid divided by volume of fluid. So now, so rho water is 1000 kg per meter cube. So and g is 9.81. And now what is the volume of the fluid? Volume of the fluid is given as 4 meter cube. and what is the weight of the fluid. So the weight of the fluid is given as m into g. We have mass into g. So this will come as 12 kg into 9.81 meter per second square. So we can cancel g with g. So here it comes 12 divided by 4 into 1000. So it is 3 by 1000, so it is 0.003. So the answer is 0.003. This is how you approach this kind of questions. So you have to, based on a given information only, you will have to select which formula to use for a specific way. Sometimes using rho into g will be useful for solving a problem, and sometimes using the basic formula, is weight of the fluid divided by volume of the fluid. So in based on the given information, you use either formula and then you can proceed to solve the numerical. And always first take care of the units. Everything should be in the SI system. So next thing is the value of 1 stoke in meter square per second. So what is stoke? Stoke is the it is a unit of kinematic viscosity. Stoke is the one second. Stoke is unit of kinematic viscosity. And what is the unit of kinematic viscosity? In centimeter square per second. So 1 stoke is equal to 1 centimeter square per second. So the question is the value of 1 stoke in meter square per second. So you have to convert centimeter square to meter square. So it is 1 centimeter into 1 centimeter. So it is 10 to the power minus 2 into 10 to the power minus 2 meter square per second. So this value is 10 to the power minus 4 meter square per second. So 1 stoke is equal to 10 to the power minus 4, which is equal to 0.0001 meter square per second. So it is correct answer is B. I hope there are no doubts till now. Okay. Now proceeding to the next question. The surface tension of a water in contact with air is given as at 20 degrees centigrade is given as 0.0865 Newton per meter. The pressure inside the droplet of water is said to be 0.02 Newton per centimeter square greater than the outside pressure. So calculate the diameter of the droplet of water. Okay. So directly going into the formula, let's know how the formula is derived for this kind of problem. So before solving, I will just shift this well. these things we'll note down later. This is not required here, I will write down later. Okay. Okay, the surface tension. First, let me. The surface tension. So let us first take a water droplet. So this droplet is filled with water. So the now thing is that so what is surface tension? Surface tension, it arises due to cohesion between the liquid molecules at the surface. So the thing is that, okay, so if we cut this water droplet into two parts, so after dissection of the water droplet, we will get something like this. So this is filled with water. And this is the whole water droplet. Now thing is that you can see that if we take any water molecule in the middle of the droplet, suppose inside, this is not on the surface, this is inside the droplet. So in that case, it is subjected to equal pressure from all sides. Equal pressure from all sides. So the molecule will be in equilibrium among but now let us consider a molecule at the surface, that is here. In that case, or you can take even here also, the thing is that in this molecule you can see so you will not consider a molecule inside, because this is a water droplet, not a water bubble. Sorry. So you can take a molecule on the surface of the bubble. So when you take a molecule on the surface of the bubble, it is being attracted by the molecules inside, but the force between the molecules of water. Suppose if we take the droplet as water, and it is given in the question, so we take the molecule as water droplet only. So the cohesive force between the molecules will be more, and outside you can see air. The attraction force between air and the molecule is much less than the cohesive force between the molecules, that is the different molecules attracting that particular molecule. So in that case, the molecules inside the droplet will try to attract the water molecule on the surface towards it, and this will create a tensile force on the surface of the droplet. So this tensile force will be coming from throughout the whole surface. So it is coming from the surface. So this tensile force is called surface tension. It is denoted by symbol sigma. Now, so the thing is that this force has to balance the pressure force that is exerted on the surface. So if we take this cross section that we mentioned, if we take this cross section, then the surface tension must balance the pressure force. So the pressure force on the whole surface should be balanced by the force by surface tension. So the thing is that when we consider pressure, we can see there is water throughout the surface. So you can see what is the area of the surface. If we take the radius of the so if we take the radius as r of the water droplet, so in that case, this is the center. if we take the radius of the droplet as r, in that case what will be the area of this surface? The area of the surface will be pi r square. So the pressure force will be acting throughout the surface, and I am just drawing this surface again here. So the pressure force, it will be pushing, it will be acting throughout this surface. So this pressure force must be balanced by the surface tension force, then only the droplet will be in equilibrium, else the droplet will break. So this pressure force, how will you calculate? So it is, let's take the pressure intensity as P into pi r square. P is the pressure intensity, and this is equal to, now the important thing, what is surface tension. So the surface tension is acting only on this surface. Remind, this is very important. So only on the outer boundary of the cross section. So it is, sorry, so the surface tension will be acting in the opposite direction of pressure. So the surface tension will be only taking place on the that is outer boundary. So it will act only on the circumference of the droplet. So if the radius is r, the circumference is 2 pi r. So we know that we have denoted surface tension by sigma into 2 pi r. R is the 2 pi r is the circumference. So we can cancel pi with pi, 1 r will get cancelled. So pressure intensity comes as 2 sigma by r. So this pressure intensity between the molecules in the water droplet, remember. So this is how the pressure intensity is dependent on surface tension. So now let's go to the question. What is given in the question? So in the question it is given that the surface tension is 0.0865. So sigma is given as 0.0865 Newton per meter, and the pressure inside a droplet of the water is 0.02 Newton. The pressure inside the droplet of water is 0.02. So this pressure, it is seen, it is called change in pressure, delta P, not P, sorry. So it is delta P. So the pressure inside a droplet of water is 0.02 Newton per centimeter square greater than the outside pressure. So delta P is 0.02 Newton per centimeter square. So this is important. Is given as 0.0 Newton per centimeter. So convert to Newton per meter square. So 0.02. So centimeter square, it is 1 by 100 into 1 by 100 into, it is 10 to the power 4 Newton per meter square. Okay. So now we have delta P, we have sigma. So we have to calculate the diameter of the droplet. So diameter is 2 into r. So if we calculate r, we can find the diameter. So delta P equals to sigma by 2 sigma by 2 r. 1 second. So 2 sigma by d by 2. So which is equal to plus delta P equals to 4 sigma by D. This implies D equal to 4 sigma by delta P is equal to 4 into 0.0865 divided by delta P is 0.02 into 10 to the power 4. So if we solve this, so let's solve this. Okay, 1 second, just move this again. Okay, so now delta 4 by 200 into 0.0865, 450 170. So the correct option is D. Diameter is 100,173 meters. I hope this is clear. Okay, if there are any doubts, you can ask me again. Okay, now coming to the next question. So this is okay. Okay, so the values of viscosity of an ideal fluid is 0. You can see this is the graph. This is on the x-axis we have rate of strain, that is rate of deformation, and on the x-axis y-axis we have shear stress. So for an ideal fluid, I have mentioned before also, it is incompressible and the viscosity is 0. So there is no shear between the fluid layers. However, then there is Newtonian fluid. So here there is linear relation between. So let's go through this graph once again, so that it will be clear to you based on the different types of fluid. So Newtonian fluid, the mu into du by dy. For Newtonian fluid, mu doesn't depend on rate of deformation, that is, it is constant, the slope is constant. So in that case, it is called the Newtonian fluid. Mu equals to constant for Newtonian fluid. Now coming to a non-Newtonian fluid, you can see there is a graph is changing, that is you can see as the rate of strain increases, the value of mu also changes. So mu is a function of du by dy. So in this type of fluids are called non-Newtonian fluid and also called dilatant fluid. Fluid also called Silagen fluid. And next comes the plastic fluid. So this type of fluids are on like it has, you have to apply only certain rate of strain, certain stress. After that only the fluid behaves, the stress will be proportional to the strain or will be varying with strain. So this type of fluids have a yield stress. This is the threshold of only if the stress is higher than the threshold, after that only the fluid will follow the property that it is linearly proportional to the rate of deformation. So this type of fluid will have a equation of this plastic fluid is mu into du by dy plus A, where A is the threshold. And last comes the thixotropic fluid. So this type of fluid, it first of all you have to cross the threshold so that the shear stress is proportional to shear strain by some relation, some non-linear relation, and the relation is given as mu into du by dy to the power n plus A. So this n is a power, so for thixotropic fluid n is greater than 1. And a classic example of thixotropic fluid is printer ink. And most of the fluids like air, water, they follow, they are Newtonian fluids. So this is a basic idea. You can if you want to learn more on the types of fluid, you can either Google, or also you can go through a standard book, that's Modian said that I mentioned, and you'll get to know. Okay, so one of you have asked what is A in plastic fluid. Okay, so the A is the threshold. This yield stress that is given, yield stress is given as A. So you can see this is a relation, this is intercept. So here stress equals to mu into, and du by dy is the x-axis plus A. If we take this formula, it is like y equal to mx plus c. M is the slope, x is whatever there is the x-axis, and c is the intercept. So in this case we are taking A, in place of c we are taking A, x is du by dy, and the slope is given by mu, that is dynamic viscosity. Okay, so the stress, yield stress, that is threshold, is given as A, it is given by the intercept, and du by dy is the rate of strain, and mu is the dynamic viscosity. So if this is for plastic fluid, if we take thixotropic fluid, then du by dy to the power some n will come, because the relation is not linear, it is non-linear. So in that case the n will come. Okay, I hope this is clear. Okay, then let's move to the next question. One second. The next question is, a hydraulic press has a ram of 30 centimeter diameter and a plunger of 3 centimeter diameter. It is used for lifting a weight of 60 kilonewton. Find the force required for the plunger. So this is a schematic of a hydraulic press. You can see this thing is called the ram. It has more surface area, and this a small thing is called the plunger. And so thing is that if we have to apply some force on the plunger, it can lift the weight on the whatever weight is placed on the ram. The thing is that one property of fluid that comes from the Pascal's law is that if you are applying some pressure at this point. So this pressure is uniformly shifted to this point. So there won't be any change in pressure in between the fluid. This comes from the Pascal's law. So this is how it is based on Pascal's law. So let us first so if we take this pressure as P1 and take this pressure as P2, then by Pascal's law, P1 is equal to P2. And what is P1? Pressure is force per unit area, that is force applied on 1 and force applied on 1 equal force applied on 2 by area of 2. Okay, so now what is given? We are given a hydraulic pressure ram of 30 centimeter. So we can find A2. Okay, just so we have a ram of B equals to 30 centimeter, which is equal to 0.3 meter. So you can, from this we can get A2 equals to pi r square equal to pi d square by 4. Okay, is equal to pi into 0.3 whole square by 4. Next, the plunger, it is given, it is the diameter of the plunger is 3 centimeter. So A1 equals to pi into 0.03 whole square by 4. Okay, so the weight on this used to lift the weight of 60 kilonewton. So 60 kilonewton is the force F2, that is at this point. F2 equals to 60 kilonewton. Now from the formula we have to find F1, that is on the plunger. F1 equals to F2 into A1 by A2 equal to 60 into pi into 0.03 whole square by 4 divided by pi into pi and pi cancel. So yeah, it will come 60 into 10 to the power minus 2 whole square is equal to 10 to the power minus 4 and 9 into 10 to the power minus 3. So it is 10 to the power minus 6. So 10 to the power equal to 0.6. This is how you find F1. Okay. Okay, then coming to the next question. One second, I am following it. Okay. Okay, now coming to question number 13. This is also based on pressure. So the equivalent head of mercury corresponding to 3 kilopascal is, take specific gravity of mercury as 13.6. So what is given? So specific gravity of mercury equal to 13.6, which is equal to rho mercury into G divided by so this implies rho mercury equal to 13.6 into rho water. So now coming to what is equivalent head of mercury corresponding to 3 kilopascal. So the pressure, if we take a column, okay, sorry, so if we take a column, it is filled with mercury. This is rho mercury and this is H. So the pressure that will be exerted by this column of mercury at the bottom so P bottom is given as rho m G H. Okay, so this is the height of the mercury, this is the rho, and this is given by the pressure formula, the pressure distribution of any fluid. So P bottom is given as 3 kilopascal. So 3 kPa, and rho m is equal to rho water into 13.6 into GH. So this will come, so we have to find H equal to 3000 pascal divided by rho water is 1000 into 13.6 into 9.81. Okay, so this will come as 3 by this 3 by 13.6 into 9.81. So how we have to calculate the height in centimeter? So this is in meter. So if we calculate, it will come, I think, 0.022 meter. 225 is equal to 2.25 centimeter. This also comes from Pascal's law. Okay. Okay, next, coming, this is a based on a conceptual question. Okay, so research question number 14 is, which of the following is an example of phenomenon of surface tension? Okay, raindrops. Yeah, raindrops is a phenomenon of surface tension, because I have done the one numerical. So if we take a rain droplet, so there the surface of the droplet will be experience surface tension, and it is being balanced by the pressure difference. Secondly, rise of sap in a tree. So if we take a tree, and if the rise of sap is based on a phenomenon of capillary action. So if we take a very thin column inside a tree, so water will be flowing up. This is how water will be flowing in the tree. It sucks water from the ground. The thing is that, so is the rise of, so if we take a small column here, the thing is that as the water is there, it will form this kind of surface. The diameter of this section is very small. Okay, just remind this, just remember this, the diameter is very small. In that case, this is a phenomena of capillary rise. So what happens when we have water in this place? The water molecules just at the surface, suppose there is no water in this part, no water, and this is water. So what will happen? So the water molecules that are at the surface, that is like just on the top of the water column, it will be attracted, it will have attracted by the adhesive force. So this will have this the small tree bark will be attracting the water molecules on the surface, because it will, the adhesive force between the tree pulp or whatever a small column we are taking inside the tree is more than the cohesive force. Just in this, you have to remember this. Adhesive force is greater than the cohesive force. So this, because of this, there will be a pull. The water molecules just near the, it will try to stick to the the material, that is a solid tree pulp, and in that case the molecules will try to rise. So there will be upward force on this water surface, and this will cause a rise in water. So this is called capillary action. So this is based on rise of sap. And a last thing is a breakup of liquid jet. So if we take a water column, and we know, suppose this is a liquid jet is coming out. So a jet is coming out. Suppose if we take this cross section, okay, so here if we break this cross section into, this is the cross section of the liquid jet. cross section of liquid jet. So if we take only one surface, that is we divide the liquid jet into two parts based on this central line. So this is R and this length is L. Sorry. So this length is L. So if we have a length L, so in that case there will be surface tension on the surface tension on this plane, and the surface tension will be balanced by the pressure force acting on the plane. So if the surface tension is less than the pressure, then in that case the liquid jet will, so the formula, there will be balance of, suppose if you take the pressure force as intensity as P into if we take 2R into L, 2R, because if we take this cross section it is D and D is equal to 2R. So I hope you have, this is clear. Like, shall I make the diagram bigger? Okay, I will make it bigger for your understanding. Take this section, okay, so this is R, R, L, R, R, L, and the pressure force is acting throughout, and surface tension will be acting only on the sides. Okay, so if we consider the balance between the pressure in the force and the surface tension, then it will come as delta P into 2R into L, because we are taking the whole cross, this is 2R into L, this is whole cross section is coming, and this is balanced by sigma into 2L. Okay, sigma, because we are working only on these sides, so L plus L, 2L. So this is where surface tension is acting. So this is the balance. You can cancel 2 by 2L by 2. So delta P equals to sigma by R. So you can see, like, if the pressure is less, in that case the surface tension will also be less. In that case the liquid jet will break. So the force won't be balanced. And in that case the jet, which is flowing softly like this, it will like diverge and break. So all the three phenomena based on surface tension. So the correct answer for this question will be all of the above. I hope this is clear. If there are any doubts, just ask. Give me a second, I will just. Coming to next question, the shear stress for a general fluid motion is represented tau equal to mu du by dy to the power n plus a. For a non-Newtonian dilatant fluid, the value of n and a. So we have seen this graph before also. See, this is a non-Newtonian fluid. So a intercept is A equals to 0, and the mu is a function of the mu is greater than 1 because it is higher than linear. So if for the sum value of dv by dy, the mu is for Newtonian is less and the mu for non-Newtonian is high. So here you can, for example, this is Newtonian and this is du by dy, and for non-Newtonian we can see that the slope is given by mu n, and this slope is given by mu n. Mu non-Newtonian and mu Newtonian. So mu non-Newtonian is greater than mu Newtonian, and also the relation is, so tau is non-linear, so n is greater than 1. So here the correct option is n is greater than 1 and a is equal to 0 since intercept is 0. This is a non-Newtonian dilatant fluid. I hope this is clear. Okay. So now let's move on to the next question. This is based on center of pressure. This is a numerical. Okay. So the depth of center of pressure for rectangular lamina of height h and width b is immersed vertically in water with its longest edge of vertical and top edge touching the water surfaces. So okay, first before proceeding to the numerical, let's have a schematic of how the question is framed. The thing is that, okay, I will just draw this thing. Here is a rectangular bar. Okay, so we have taken a rectangular bar. The height is given as h and the width is given as b, and it is immersed vertically in water with its longest edge vertical and top edge touching the water surface. So this is the water surface and the top edge is touching the water surface. So what we have to find? We have to find the depth of center of pressure. Okay. So listen carefully. So the thing is that the pressure that is dependent on Pascal's law is that at each point the pressure is dependent on height. So at this point, if we take as h1, the pressure will be rho g h1. Density of water is rho, and if this is h1. So at this point, if we take from the surface, the height is h, so the pressure at this point is rho g h. Okay. So to find the center of pressure, we have to use the formula of method of moments. First, let us take to find us the main phenomena is that when you take the center of pressure, it's like you're taking one unified pressure. So you take one pressure value, suppose at some, this is P, so this is Cp, center of pressure. It is, suppose, let's say h1. So it is, the center of pressure is at a height of h1 from the surface. So if we take total pressure on the vertical surface of the bar, it should be acting on the center of pressure, and this we have to equate to the total pressure that is being distributed throughout the fluid. So the pressure distribution is given as like this. Okay. So this is how at this surface the P is equal to 0, at here P is equal to rho g h. Now, so what will be the area of this triangle? Area of this triangle is half into base into height. What is the base? Base is rho g h into height. Now, okay, so this is one thing, area of the pressure triangle. Now suppose what is the total pressure that is acting on this surface. So we are taking this surface, suppose S1. Total pressure on surface S1. So this total pressure will be what? Suppose at each point you are having some pressure value, suppose rho g h1, rho g h2, rho g h3, like that, is small. So it is the integration of all the pressure values. Why integration? Because pressure is not discrete, so it is a continuous, it is varying continuously, so we have to use integration. So total pressure is given as integration of 0 to h rho g rho g. Suppose we take this height as something like what? Let's take the value as L. Pressure at height L, and this is density rho. Okay. Pressure at the height, like depth L from the surface, and we take a small element that is of length dl. So if we integrate the pressure in the small dl elements from height 0 to height h, we will get a total pressure acting on the surface, right? So rho gl dl. Okay. So the thing is that to find the center of pressure, we have to use the method of moments. That is total pressure, the moment that is being applied by this total pressure on this plane is, let's say, OO. Total moment about plane OO must be equal from both criteria. So what are both criteria? Both criteria is, one, we have taken the pressure distribution, and the second, we have taken P. One second, sorry. Criteria 1 and this distribution, and the second criteria is center of pressure. So the center of if the second criteria is center of pressure, so total pressure is P equal to this P. Okay, we have found this P based on half rho g h square. So this total pressure into, we have taken I think H1. This total pressure exerted by this triangle is P, is given as P, which is equal to half rho g H square. This is the value, and half rho g H square, and this total pressure will be acting at the centroid of the triangle, right? So the centroid we take as, the centroid, or this will take as the center of pressure. So center of pressure is at a height of H1. So this total pressure from this triangle will be acting at the center of pressure. We take as a unified one point, single point. So we take as H1. So this is the moment from center of pressure criteria. Okay, and the moment from this criteria will be equal to what? So okay, one thing I just note down. Okay. I'll write this again, sorry. Moment from center of pressure half rho g H square into H1 . Okay, the second criteria is pressure distribution. So in that case we have taken what you have seen. This is the suppose vertical bar. We have taken an element dl, it is from the length L. So this small element will be exerting suppose some pressure dp at this surface, and the moment is what? So the dp will be rho g L. What will be the moment? Moment about this plane O. It will be rho g L into L, because the length is L. Okay. So this the moment about this surface OO will be rho g L into L, and this moment we have to integrate for all the elements. So one element will be here, one will be all the continuous elements till we reach the bottom of the vertical bar. So total moment will be equal to, we have to integrate from 0 to h. What? So this is not dp, this is dm equal to rho g L into L, and into dl. dl is the what element width. So we have to integrate dm from 0 to h. So this will be 0 to h rho g L square dl. Okay. So the both the moment, this is number 2 and this is 1. So both the moments should be equal, because we are taking finding a center of pressure. So the total moment exerted by the whole element should be equal to the distribution of the moments, like moments exerted by the small pressure distribution, because this is how we find the center of pressure or the phenomena of centroid for a like solid body. So both be equal. So what will this give? This implies half rho g h square into h1 equal to 0 to h rho g l square dl. So rho g can come out, integration of 0 to h l square dl rho g l cube by 3, sorry, from 0 to h rho g h cube by 3. So rho g will be cancelled, we can 2 1 h will go, so this implies h dash equal to 2h by 3. So this is how the center of pressure. So this is how the center of pressure is derived. So the correct answer is 2h by 3. So is there any doubt in this derivation? If you have any doubt, you can ask me now. Okay, thank you. So yeah, let's move forward. 1 second. So these are some questions from like previous assignments from like last 3-4 years. So I have few more like some basic questions. Let's proceed to that. This is a question from Modi and Sheth. Okay, the kinematic viscosity and specific gravity of a certain liquid are 5.58 Stokes and 2 respectively. Calculate the viscosity of liquid in both metric, gravitational and SI units. So let's solve this question. First is metric units. So here it is given that specific gravity is equal to 2, and you should remember there is no units for specific gravity, and kinematic viscosity nu is equal to 5.58 Stokes, which is equal to centimeter square per second. Okay. So this metric units are used in English system, so it's not like we won't be using, and generally in our Indian system. In India we mostly use SI system only, but still for your knowledge I will be like giving the description here. So in this unit the rho is given as 102 MSL per meter cube, and since the specific gravity of the fluid is rho water, okay, rho water is given as 102 MSL per meter cube, so the rho of the fluid is given, it will be 2 into 102 based on specific gravity formula. Okay, and the kinematic viscosity is given, so now mu equal to it will be given as nu into rho, where nu is 5.58 into 10 to the power minus 4 meter square per second, and we have to multiply with rho, that is 204, and this will give the units in kg feet kgf second per meter square. So the value will be 0.114. So this is one thing. And now secondly, SI unit. In SI unit it is very simple. So specific gravity equals to 2, rho water is equal to 1000 kg per meter cube. So the mass then density of fluid will be equal to 2000 kg per meter cube, and nu is given at 5.58 into 10 to the power minus 2 meter square per second. And so therefore nu we have to calculate. Nu will be equal to nu into rho, and it is be like 5.58 into 2000 Newton second per meter square. So this is equal to 1.116. This is in SI unit. Okay. So this is just for information how like you can do calculations for both units. Okay, here is a sample problem I have picked up. I will just give demonstration. This is solved in Modi and Sheth. So a 5 meter cube of a certain oil weighs 4000 kgf. The calculate a specific weight, mass density and specific gravity of the oil. The specific weight is given as weight per unit volume. So weight is given 4000 and the volume is given as 5 meter cube. So it's very simple, 4000 by 5, 800 kgf per meter cube. So what is the mass density of the mass density means rho. Rho is equal to specific weight of the oil divided by g, specific weight, gamma by g. So we have found gamma in the previous part. So gamma is specific weight 800 kgf per meter cube divided by rho of g is 9.81. So you can get 81.55 msl per meter cube. And similarly, specific gravity of the oil is specific weight of oil by specific weight of water. So it's 800 we have found out here. Sorry. And specific weight of water we know 1000. So 800 by 1000 is 0.8. And okay, this is the last question I am solving before. Here suppose a plate of 0.024 millimeter distance from a fixed plate moves at a 61 centimeter per second and requires a force of 0.2 kgf per meter square to maintain this speed. Determine the dynamic viscosity of the fluid between the plates. So let us first just draw the diagram. This is a fixed plate, V equal to 0, and this is a moving plate, V equal to 61 centimeter per second, and the distance between the plate is 0.0254 millimeter. Be careful of the units. Sometimes they are using centimeter, here they are using millimeter. And the force equal to 0.2 kgf per meter square. Determine the dynamic viscosity of the fluid. So let us will consider Newtonian fluid here. So if you consider Newtonian fluid, the shear stress for Newtonian fluid is given as F by A, that is equal to mu du by dy. So in this case we will replace this by mu into V by y. So v will be, because here v is 61, here v is 0, and y is the y is the gap y is the gap between the plates. So you just need to use the formula, but before using the formula you have to be carefully change the unit. So v is equal to 61 centimeter per second. Let's convert to meter. 0.61 meter per second. Y is equal to 0.0254 millimeter. So let's 0.02 into 10 to the power 3 meter. So let's take 254 into. Now so tau is given as 0.2. So let's use the formula. 0.2 equals to mu into 0.61 divided by 254 into 10 to the power minus 7. So this implies mu equal to 0.2 into 254 into 600, and this will give the value of mu, I think this one, 8.3 into 10 to the power minus 10 kg of second per meter square. Okay, so I have solved around 16 questions. So if you have any other doubts like related to these topics, like whatever is being taught, you can ask me. We have like I think 10 minutes left. Any other doubts or anything you haven't understood? Hello? So no doubts at all. So which question? Last two questions, like it is just based on units, I think. So specific weight, mass density, and specific gravity, these are just based on formulas. So what exactly do you want to know? Yeah, this question is just based on volume. Volume is given, your weight is given, so it's like you have to use a specific weight. It's weight of the fluid divided by volume of the fluid. The simple formula. We are not doing anything rocket science here. So it is very simple. It's just the units. The units kgf is like a metric gravitational unit. So they have used different units. You can convert that to a new SI unit also if you want to solve in SI unit. But since they have given all the values in that unit, so I haven't changed the units to SI. It's just simply substituting the values whatever they have given. Again, mass density is rho. Density is given as specific weight divided by acceleration. So I have explained before also, specific weight equals to rho into g, which is also equal to weight divided by volume. What is weight? Weight is m into g divided by volume. And what is mass? Mass equal to rho into volume into g divided by volume. So volume gets cancelled, so specific weight equal to rho into g. So if you need to find if rho, then rho equal to specific weight divided by g. That is what they have used in this formula, rho equal to specific weight divided by g. And then specific gravity specific weight divided by specific weight of the oil divided by specific weight of water. That's how it is calculated. And here I have explained, so this is tau is given, tau is the force per unit area, that is they have given 0.2, no, they have given tau here, okay, sorry. So tau is force per kgf per meter square, force per unit area is given. So mu into du by dy, but we have considered that the slope is like linear. Slope is linear, so du by dy is simply by v minus 0 divided by y. Okay, this is y, v minus 0 by y, that is y mu into v by y. V is given this one as 61 centimeter per second, y is given 0.0254. So we have just substituted change the units and then solve the question. So yeah, if there are any other questions you can ask me, else I will end this session. And yeah, I will share this video in YouTube. If you need if you have any other doubts later, you can ask me in the next session also. Okay, thanks for attending, and yeah.